discussing a presentation by Trevor Darrel. He's a professor at Berkeley. Presentations in the show notes. So he's a pioneer in robotics. In particular, I would say the importance of Trevor is that he really is a pioneer of what today is called end-to-end training. Now, he doesn't necessarily call it that way. He's actually making an effort in this presentation to go away from pixels only into something, what he calls trajectory prediction, point tracking. I'm going to talk about this in a second. But my point here is that he, and I think his collaborators at Berkeley with, Peter and Sergey and others, they really have pioneered this approach of pixels in, actuators out. And he actually says it in the presentation. He says that this approach, other than maybe at industrial scale, doesn't seem to work that well. What he means is, of course, Tesla's approach, pixels in, actuators out. He says the juries are still out there. Now, we'll see about that. But again, I think that's one thing I appreciate about him. Now, there's a couple of things that he talks about here. I want to focus particularly on two things: the world models and the mimic from video. That's I think that's actually probably the most important piece of the presentation. And what I mean with that is, mimicking from video is potentially the path towards training humanoid robots at scale. And if we listen to, let's say, what Elon Musk said recently on one of the podcasts that he was on, he spoke about that. He said, he was asked, how are you going to train Optimus? He said, we're going to do it like Tesla. And meaning the Tesla FSD. And it wasn't exactly clear what he meant with that. We believe what he means is we're going to do the same exact thing. We're going to take, massive scale human data and train the robots mimicking humans. Now, Trevor mentions that. He calls it mimic the model. It's in the show notes. But he says that one of the problems with that approach is that the robot is trained to mimic the human, but only in the environment that the human is in. And the problem then is, how do you generalize that? How do you generalize from a robot walking up the stairs at Berkeley towards a robot walking up the stairs anywhere else? So that's one of the issues. Now, you could argue that maybe the robots could be actually trained within the environment, let's say within a factory, to move around and do work. But of course, that's kind of almost, well, there's a bit of a lack of generalization here, because you run the risk then of only having the typical behavioral cloning problem, which is that you only do or know to do what the humans did that you're mimicking, and that's probably not going to be enough. But nevertheless, I think that's one of the interesting parts of the presentation. He also talks about the architecture here. So you have, the ego capture. Let's say you're a scientist doing work in the lab, and you have a GoPro on, basically capturing the ego version of what you do, and then that gets translated into 3D representation of human pose, which is work that is particularly also interesting at Berkeley. I think Jitendra Malik does a lot of that work. Peter does that work. So what you want to do is, like, once you have a pose and once you have a certain initial frame, then you want to run a video with potentially what the human will do, and you can maybe also predict certain poses just using 3D reconstruction of human pose. So that's the mimic part. He then talks about the world model part, which is actually pretty interesting. That is something he worked on with Jan LeCun. That's all the rage now, also because of Fei Li's World Labs World Labs business. So the idea there is the almost the opposite here. So you're not training from humans. There's no behavioral cloning here. What you're trying to do is predict the next state given a current state and an action. And that's in itself, of course, very interesting. That gives optionality to run many rollouts and therefore improve the the data scaling and have more edge case design. For example, you can have different trajectories and run edge cases given uh, given actually real world data and then run edge cases. That's something that Ashok talked about in one of his recent presentations, where they take real video models and then reconstruct trajectories based on the real videos, fully generated trajectories. So based on visual, variational autoencoders, taking just realistic probabilities of what could happen next. So those were the two main things he spoke about. He then spoke about a four-dimensional tracking. They call it Star Trek, Star 4 track or something like that. Papers in the show notes. What they're doing is they're taking pixels in, but they're doing trajectory planning. And I think trajectory planning is the key. I think he comes to that point also towards the end of the presentation. He says the biggest problem in robotics, in vision, is actually it's correspondence. Correspondence being, okay, which pixels belong to which position throughout the video, and which pixels are in the same position, and how do we know? How do we know which pixels belongs to what and where in which sequence of the video? That's an old statement out of the computer vision community going way back, and I think it's still prevalent now. We could argue that some of that is solved. I mean, all of us who use Tesla's FSD probably have a sense that correspondence is solved. The robot, i.e. the car, knows pretty well what to do at any point in time. So that's probably, you can say, the correspondence is solved. Nevertheless, I think what Trevor's trying to get there with his models is, of course, also, can we get better models without industrial scale data? That's the key, because in actuators out at a scale of a Tesla, for example, but can we do it maybe with less data and more efficient models? And I think that's the trajectory that he's on. One last thing I just want to mention, which is really interesting, is he calls it de-halucinating a model, and I think there's an interesting insight there, and that is he talks about the idea that you have, let's say, when you prompt an LLM and it gives you a wrong answer, you can then tell the LLM, are you sure about that? Maybe you want to reconsider. And then the LLM actually reconsiders and says, yeah, well, I'm sorry, I was wrong. So they're using that concept, and they're training a model with confidence tokens. And the way they do this is they literally create synthetic data where they take a model, they put, let's say there's a dog here, and then they put a confidence token, and then they do the same, let's say, image, and they say there's a cat here, and they don't put a confidence token. And then the model learns that when it's confident, it has a confidence token, and when it's not confident, but when the probability distribution that it's predicting doesn't make sense, it doesn't have a confidence token. So it kind of learns to be more confident or pays attention better to what's relevant. I think I don't fully understand the idea, but I think I understand the idea. I don't fully understand the technique, the engineering behind it, but I think the idea is really interesting, that you can actually dig a little bit deeper into a model and often get the right answer. That means, what that really means, what the confidence tokens actually mean in technical terms, is they simply reflect a probability distribution that is maybe not so fully clear. So you kind of reground the model into, okay, look, if you're not really sure whether there's a dog or a cat here, I'm going to give you a confidence token for dog when there's a dog in there. And if there's no confidence token, then that means it could be maybe a cat or not. But if there is a dog, you're going to have a confidence token with the dog. Something along those lines. Reinforce what's sure, get more certainty in the model. So I thought that was just interesting. So to summarize, Trevor Darrel is somebody I follow very closely. here at Orange Capital Partners, we follow academia. We are at the crossroads of academia and technology, where technology turns into products and services for wealth creation. That's our goal. That's where we live. That's why we spend a lot of time with academia. And I think Trevor and his collaborators at Berkeley are a very good example of how academia can turn very quickly, actually, into leverageable wealth creating products. In particular, the humanoid robot revolution, which is already now starting with FSD and Tesla, where the end-to-end training, the pixels to actuators actually has been delivered. And there's actually a product now, something that Trevor and his collaborators pioneered. Thank you.